Let's talk about Hess's law and look at a couple of examples of Hess's law for just a few minutes. Hess's law is a way of taking enthalpies from several reactions and adding them together so that we can find the enthalpy of some new reaction or some net reaction. We just add the equations up and we add their enthalpies together, and whatever is there as products and reactants, if that reaction actually occurs, that will be the enthalpy of the reaction. So there are two rules you have to keep in mind. If you change the direction of a reaction and just reverse the reactants and products, write the reaction the other direction, you change the sign from positive to negative or negative to positive. That's the sign of the change in enthalpy for that reaction. You can also multiply or divide reactions so that you get the correct, the number of species that you need to add up to the final reaction you're looking for. And so if you multiply or divide, the change in enthalpy has to also be multiplied or divided by the same number. So, for example, page 244 in your textbook has this reaction. And I think it's always helpful to focus on what reaction you want to come out with at the end of your process, because that is always a goal, that you have some reaction and you don't know the enthalpy of that reaction. Maybe it's even kind of impossible to carry that reaction out, but if it did carry out, what would the enthalpy be? And so that's what this allows you to do. Now, you were given here two reactions. These two reactions for carbon in the form of graphite being combusted and providing this much energy, negative 394 kilojoules of energy coming out of that system. And out of the system where we take diamond and do the same thing, we get out just a little more energy, negative 396 kilojoules of energy released. So, when I start to work on making this reaction up here my goal, I'm going to use these reactions that were given to me in the problem. So the first goal I'm going to focus on is I want graphite as a reactant. Well, here I see graphite as a reactant, so I'm just going to rewrite that equation. Carbon in the form of graphite combines with oxygen to produce CO2 and the change in enthalpy of negative 394 kilojoules. Now, up here in my goal, I want diamond as a product. I don't have diamond as a product. I have diamond as a reactant. What can I do to get diamond as a product? That's right. All I have to do is reverse the reaction, and diamond is now a product. So I reverse the entire reaction. I rewrite it CO2 yields oxygen and carbon in the form of diamond. But I also have to change the enthalpy on that reaction when I do that. So now I'm going to add these two reactions that I've rewritten here in red. I'm going to add those reactions together the same way we've added reactions together in the past. We're going to just bring down all the reactants and products that don't cancel out. So here you'll notice CO2, and that, by the way, is CO2 in the form of gas. Those are in the same form, so they can cancel out. Here I have oxygen. This is oxygen in the form of gas, so they both cancel out. So the only thing that's left now is carbon in the form of graphite is being changed into carbon in the form of diamond. And to get the change in enthalpy for that reaction, I just add these reactions together. So that is a very easy example of Hess's law. Let's see if we can find one more example. This is on the next page in your textbook, page 245. And as you follow along here, it may help to have your book open to that. page 245. This is our goal. Remember, always work these problems with your goal in mind. So I'm going to start writing equations that I have available to me so that first of all I get a couple of borons here as a reactant. Here's a reaction with a couple of borons as a reactant. Ah, that's good. I have that first goal kind of taken care of. Now I'm going to look for something with hydrogen as a reactant. In fact, I need at least three hydrogens. So where was hydrogen a reactant? Well, if we go down, I think it's equation C, listed the way it is in your book. It's listed the same way here. Hydrogen is a reactant, but I need three of those hydrogens. How do I do that? Well, I'm going to have to multiply this equation by 3, which also means I have to multiply the change in enthalpy by 3 when I go to calculate the answer. The next thing in my goal that I'm going to kind of focus on is I need to get B2H6 as a product. Now when I look at my possible reactions, I see reaction B that's listed there in the book. That is has B2H6 as a reactant. So I have to reverse that reaction, making B2H6 a product. And I have to change the sign on the enthalpy and make sure I have 2035 kilojoules as the enthalpy of that reaction the way it is written. So we start adding these together and making sure things cancel out so that we don't have anything extra. We only want the stuff that's up here in our goal. Let's see, B2O3 cancels out. Here I have 3/2 oxygen and 1/2 oxygen. That's 4/2 oxygen. Oh, wait, I have this 3. Don't forget this 3. So that's actually 3/2 oxygen and 3/2 oxygen there. Those are going to cancel out. So my oxygens are taken care of. And I'm looking here to see if I've missed anything. Okay, here I have water in the form of gas, and here I have water in the form of liquid. Those are not exactly the same thing. It takes a different amount of energy. Water in the form of gas has a different amount of energy than water in the form of liquid. They don't cancel. That's why we were given this third reaction, and we have to rearrange it and multiply it by a coefficient so that these 3 waters represented here in the form of liquid can cancel these 3 waters that are in the form of a liquid. So now those will cancel, and the change in enthalpy that we have right here takes that change in enthalpy into account of the difference between gas and liquid water. So here I have 3 waters once again in the form of a gas, and here I have 3 waters in the form of gas, and they cancel or factor out. Now I just need to add these together, the product of 3 times this enthalpy and 3 times this enthalpy, add it all together, and I should get the change in enthalpy for this original reaction that was our goal. And that change in enthalpy is 36 kilojoules for that reaction the way it's written. Well, that's Hess's law, and we will enjoy some more problems with that, I am sure.